So we are now starting Unit 5, and we're going to start off with the extreme value theorem. So this is a pretty easy concept, but it's a little bit new, and it's going to build on what we know about relative extrema. So relative extrema, right, extrema meaning a max or a min, was where we changed from increasing to decreasing. In the absolute extreme, that's going to be the very, very highest point or the very, very lowest point. So if we kind of look at these two graphs here, we're going to start off with f of x, the graph on the left. If we look at where does this graph change between increasing and decreasing, it would change at -3, at -1, and at 2. So x equals -3. That's and basically +2. Those are our relative minimums. And x equals -1. That's our relative maximum. Right? If we wanted the full coordinates, I guess we would say right, -3, 0, 2, -6, and then we could have -1, 3 for our relative max. So those are our coordinates. Then on the domain of f, what are the coordinates of the absolute extrema? So the very, very lowest that this graph ever gets is at -6. So -6, 2, -6, right? We got to write it correctly. 2, -6 is our absolute minimum. So we can abbreviate that absolute minimum. If we look, this graph on both sides goes up to infinity, right? It's coming up to infinity and up to infinity. So there is no absolute min. So there's no, maximum. There's no absolute max. Right? There's no biggest point because it goes up to infinity and infinity goes on and on forever. Then on this next graph, we'll do the same thing. I'll use another color. So our relative extrema, right, is any time it changes. So we'll say that's -3, -4. And then we have -1, +4. And then we'll have 3, 2. So -3, -4, and 3, 2 are relative minimums because they changed from decreasing to increasing. And -1, 4 is a relative maximum. Right, but then if we look at our lowest point, what's our very lowest point? Our lowest point is -3, -4. So that's our absolute minimum. That's the lowest this graph ever got to. Right, even though 3, 2 was a relative minimum, it's not the very, very lowest. It's only a relative. It's minimum to kind of what's around it. It's below what's around it. That's why we call it relative. Relative meaning compared to what's near you. And then our absolute maximum is actually here at 5. So that wasn't even from a relative maximum. We think that was actually from the endpoint. So 6, 5 is our absolute maximum. So on the domain of the function, did the absolute extrema occur at the function's relative extrema? And our answer to that is kind of sometimes, right? 2, -6, that was also a relative extrema. And -3, -4, that was a relative extrema. But 6, 5 was not, right? 6, 5, this was an endpoint. And then over here, we had none. So we had kind of none. So sometimes they do and sometimes they don't. So kind of what we'll say is the absolute extrema can occur at a relative extrema, but it doesn't have to, right? So like our other options, or our three options could be a relative extrema, it could be at an endpoint, or there could be none. Those are kind of like our three options, right? So here we'll kind of look again, and we'll do this kind of quickly. So looking at here, what are our relative extremas? So -3, 0, and you guys could pause the video and try these on your own if you want to. And 2, -6, those are our relative mins. And then it's the exact same graph. Yeah, I think this just got copied a little bit bad. Oh, no, I know what I did. I changed the interval. Okay. So this was, sorry, I misread this. We'll restart this one. So don't be like me and just assume it's the exact same question. I haven't taught this in too long. So on the interval from -2 to 3, so just between -2 and 3, right? So now we're basically just saying we're going to look at from -2 to +3. What are our relative extrema? And so what I do is anytime I have a closed interval, I'll kind of make an X and a Y chart. And the points I use are, I use any relative extrema, and then I also use our endpoints. So the endpoints are also important to use. So I'm going to use our endpoints. So -2 and then at 3. So we're going to use -2, -1, +2, and 3. So the -2 and the 3, those come from our endpoints, right? So the y value at -2, I know it's kind of hard to look at it, but here we can see it better right here. -2 has a y value of +2, and at 3 we have a y value at 0. So at -2 we're going to put in +2, and at 3 we're going to put in 0. Then for our extrema, right, at -1 we were at 3, and at +2 we're going to be at -6. And so this really helps us to figure out those absolute extrema. So we'll say that 2, -6, that's our absolute min. And then our highest values at -1, 3. We're looking at the y values, right? The biggest y value and the smallest y value. And it is important here you want to put both the x and the y when possible for these absolute extrema. Okay, now for the interval -4 to 1, we're going to do the same thing. But now we're going to use -4 and 1 as our endpoints. So if we look between -4 and 1, I'm going to kind of get rid of that. So from -4, our y value is +4. And at 1, our y value looks like it's at -3. And then now we want to look at kind of in between that section of the graph, what critical points do we have, right? What critical points do we have? We always want to look at basically our endpoints and our critical points. So our critical points are at -3, 0 and -1, 3. So our absolute minimum will be at 1, -3, and our absolute maximum will be at -4, 4. So they were actually at both of our endpoints, which is interesting. Okay, and we'll do the same thing over here for this guy. And so for this guy, on the interval from -4 to 5, so -4 to 5, we're kind of looking inside there. So we're going to put in, for our XY chart, we're going to put in our endpoints, so -4 and 5, and then we also need to put in any critical points. So our critical points were at -3, right? It's the x values for these, because we're on the x chart, and then at -1, and then also at 3. So now we're going to just fill in our y values. At -4, our y value is -1, -3, our y value is -4, -1 is +4, at 3 we're at +2, and at 5 we're at +4 again. So in this case, -3, -4. -4 is our smallest y value, so that's going to be our absolute minimum. And we have two absolute maximums because it hit 4 twice, and that's okay. So -1, 4, and 5, 4 are absolute maximums. So we have two of them, and that's okay. And then we'll go from -2 to 6. So we're just going to kind of change this interval. So I'm going to go ahead and erase this. And from -2 to 6. So again, we're going to make our XY chart. And -2 and 6 are our endpoints, so we always start off with those. And we have two critical points here. We have two critical points. We have at -1 and at 3. So at -2, our y value was at 0. At -1, we were at +4. At 3, we were at +2. And at 6, we're at +5. So now -2, 0, that's our absolute minimum. That's the smallest y we get. And 6, 5, that's our absolute maximum. That's our biggest that we can get. So making that chart really, really helps. And so we have this question, when the domain is restricted, to a particular interval, at what places, at what three places that could that absolute extreme exist? And it's kind of that same thing. So number one, it could exist when, at an endpoint. Number two, it could exist when f prime of x equals 0. And number three, it could exist when f prime of x is undefined. And so these, right, are our critical points. So essentially they can exist at critical points or at endpoints. Now, it is important both of these graphs were continuous within the intervals we were looking at, right? Inside of those intervals, they were continuous. So that's an important concept for the extreme value theorem. So if f of x is continuous on the closed interval a to b, so it doesn't have to be continuous everywhere, but between the endpoints, it needs to be continuous. Okay. Then, the comma there, f of x has at least one absolute max and at least one absolute min on the closed interval a to b. So that's all that the extreme value theorem tells us. It doesn't tell us how to find them. It just tells us the extreme value theorem is actually very, very basic. It only tells us if f of x is continuous, then there has to be one absolute max and there has to be one absolute min. Now, what I kind of want you to add is kind of our process whenever we see the words absolute max or absolute min. Our process is always the same. So it's very similar to the relative minimums, where we start off by basically setting f prime of x equal to 0 or undefined if it's a fraction, right? Because that's finding our critical points. And then once we do that, though, instead we don't need to make a number line. So the old way, with relatives, we make a number line. We don't need to do that for absolute. For absolute, instead of making a number line, we make an XY chart and we put in our endpoints. And then we put in our critical points. And we see what is the biggest y, what's the smallest y. So that's the process. That's not what the extreme value theorem says, but that's how we find the extreme values, the absolute values. So if we didn't have a graph and instead we had a function, let's look at how this would look. So they might say, determine the intervals where f is increasing and decreasing and justify this as review, right? F prime of x equals negative 3x squared minus 12x minus 9. Set that equal to 0. A lot of you guys tried to jump straight to the x method. Don't do that here. See if you can factor out a common term first, always. So we can factor out a negative 3. That's going to make this so much easier to factor. But don't divide by negative 3. Don't do that, because the negative 3 is still going to determine our increasing and decreasing. So it needs to stay there. Then we're going to have x plus 3 and x plus 1. So this gives us x equals negative 3 and negative 1. Now, when we're doing increasing and decreasing, we still make a number line. Even relative max and relative min, we still make a number line. The only new thing is going to be for the absolute value. So if we plugged in negative 4, right, we're going to get a negative at negative 3 always. Negative 4 plus 3 is negative. Negative 4 plus 1 is negative. Negative times negative times negative is negative. If I plug in negative 2, I'm going to get positive right there, and so this will turn positive. If I plug in, say, 0, I get positive and positive, but negative 3 times that is still negative. So decreasing, increasing, decreasing. So we've done this enough. Negative infinity to negative 3, union negative 1 to infinity would be decreasing, because f prime of x is less than 0 for those intervals, and negative 3 to 1, negative 1 will be increasing, because f prime of x is greater than 0 for those intervals. Okay, determine our coordinates. So x equals, now if it says coordinates, not of the x values, but the full coordinates, then x equals negative 3 is our relative minimum. right? Because f prime of x changes from negative to positive, and x equals -1 is our relative maximum. Because f prime of x changes from positive to negative. I'll let you guys write that, but we've done it so many times. But when it says coordinates, we actually have to plug these back in. So you have to plug these back in. So, f of -3, that would be -3 cubed minus 6 times -3 squared minus 9 times -3 plus 2. And you can use your calculator for these if it's calculator active or on the homeworks. I'm fine with that. Or you can do them by hand. So this will end up being 56. So instead of putting x equals -3, we're actually going to want to put -3 comma 56. And then for -1, right, -1 cubed minus 6 times -1 squared minus 9 times -1 plus 2. That's going to be -1 minus 6, right, because the square turns it positive. This one was actually, sorry, positive 1, because that's, yeah, I may have messed up on this last one, actually. Let me double check. Yeah, I totally butchered my signs. So this is why I use a calculator, be careful. So -3 cubed is -27, but then times this negative will turn it positive. And then -3 squared is +9, but +9 times -6 is -54. So actually 27 and 27 make 54. Minus 54 goes away. So this was 2. If you used a calculator, then you should have gotten that. And then on this last one, that'll be +1 minus 6 plus 9 plus 2. 9 minus 6 is 3, plus another 3 will give us 6. So what we'll say is, instead of saying x equals -1, we'll say -1 comma 6, that's our relative maximum, and -3 comma 2 was our relative minimum. So, I guess use a calculator, be careful with your arithmetic. So now pictured is the graph of this function, and we see it graphed, but we wouldn't even need to necessarily have the graph. We would need to just kind of know the coordinates. So the graph is just going to help us to quickly kind of plug in. But in between -4 and 1, so we're going to make our xy chart. We're going -4. Now, -3 is a critical point, and -1 is going to kind of change into our endpoint, right? Because we're going to put our endpoints in there and then any critical points in between. So at -4, we can see from the graph we're at 6. If we didn't have the graph, what would we do? We would just plug in -4 into the equation, right? And I'll kind of show us on the calculator how to do that fast at the end of this video. -3 we already plugged in, we got 2, and -1 we already plugged in and we got 6. So our absolute maximum, we have 2, would be at -4 comma 6 and at -1 comma 6. So we'll use both of them. Then the absolute minimum, we already have our table, will be at -3 comma 2. Right, so I'm not going to rewrite the table, we already have that written out for us. So then identify the absolute maximum on the closed interval from -4 to +1. So be careful, that's +1. Okay, so x and y. So now we're going to have -4 and +1. And then we also have our critical points. So -4 we already saw was 6, -3 is at 2, -1 is at 6. And then at 1, we're way down here at -14. That's our y value at 1. So our absolute maximums are the same. They're still -4 comma 6 and -1 comma 6. But now our absolute minimum is now at 1 comma -14. And so that's kind of how we do that. So using this extreme value theorem, how would we do this with algebra? And so basically, if we didn't have the graph, well, we did the same kind of thing. So I'm going to skip, basically we're going to set this equal to 0. We already did that by hand. We got -3 and -1. But if we wanted to do it without a graph, let's say we didn't have a graph. So if normally these are on calculator questions, and if they're not, you'd have to do it by hand, but normally these are calculator questions. So we're going to make an XY chart. We're going to put in -4, -3, -1, and that's it because that's our endpoint. And so on a calculator, by the way, just so we could kind of see this, is well, if we needed to find those critical points quickly on a calculator, what we can do, I'll show this step, is we could take the derivative, right, with respect to x, and then we can go Control C here, and then Control V. So we can do that, and so that's our derivative. And then what you can do is you can go to Menu, Algebra, Solve, and we can solve for this derivative equals to 0, comma, x. And so that gives us the -3 and the -1. Those were our critical points. Now to plug them in, we go back to the original. So we go back to the original, and we put Control equals, and we go to the at, and then we say at x equals, now we're going to start off with our first endpoint. So it's x equals -4. Right, we get 6. Then we can just come up here and change it to -3. And we can come up here and we can change it to -1. Now, we got these same values on the graph when we did it with the graph, but you know, it's important to be able to do it with the calculator as well. So we had 6, 2, and 6. And so now, you know, we're using this to find our absolute max. So -4, 6, and -1, 6 are our absolute max. And -3, 2 is our absolute min. And so that matches up with how we did it on the graph, but I just wanted to show us how would we do it on a calculator. So same thing here, and this is all the work you would need to show if you're using a calculator. You just say f prime of x equals 0. You don't even have to show any work by hand, right? Because they know that we can use our calculator for this. So what we did on our calculator is we found, you know, the derivative, and then we set the derivative equal to 0. And then now we're starting to plug in our points. So the difference here is just that the endpoint changed. So now we have x and y, -4, -3, -1, and now +1. And so now we need to also come up here and change this to a +1. And so that's kind of how this works. So we get -14. Sorry, yeah, -14. So now -4, 6 and -1, 6, those are absolute max. And 1, -14, that's our absolute min. Okay. Now, for each of these, state why the extreme value theorem is applicable or not on the interval from -5 to 0. So remember, the key for it to be applicable, that's what the if was. It was if f of x is continuous on the closed interval a to b. Well, in this case, it would be -5 to 0. So here, basically, x equals -3. That's, you know, that denominator, we would get a vertical asymptote there. That's where it's discontinuous. So here, extreme value theorem is not applicable for -5 to 0 because h of x is not continuous at x equals -3. In this one, anytime we have a square root, you set the inside of your square root to be greater than or equal to 0. So x has to be greater than or equal to 3. So any values greater than or equal to 3, that's our domain, right? You know, here our domain was x cannot be -3. Here our domain is essentially x is greater than 3, or basically 3 to infinity. So it would be with a bracket. Now, that means everything from -5 to 0 doesn't exist. So here, the extreme value theorem is not applicable to h of x. And we could even say because g of x, this was g of x, is continuous only for 3 to infinity, or you could say x is greater than 3, equal to 3. And so -5 to 0 isn't in that interval. Here, ln's, we take the inside of an ln, we set that to be greater than 0, just greater than 0, right? ln's, that graph looks like this. So it's only when the inside is greater than 0. So here we get x is greater than -7. So anything greater than -7 is part of our domain, right? And so that means it is continuous. So here, extreme value theorem does apply because f of x is continuous over -5 to 0. So it's because it's between -5 and 0, right? And what our domain is, you know, essentially from -7 to infinity. that's part of our domain, and negative 5 to 0 is part of that, right? And if you want to add, because f of x is continuous for x is greater than negative 7, you can add that, right? So that's part of that. Now, coming here, given these functions, we want to determine if these are extreme value theorems. We're going to do these actually for our warm-up tomorrow. So if you want to get a head start, you can. But that process is the same that we did up here, but now using our calculator. These are calculator active. So your first step on all of these is going to be to set f prime of x equal to 0. And the way you do that on your calculator is kind of 2 steps. You can do it in 1 step if you're really advanced, but I like to do it in 2 steps. Is do first d dx, and secondly, use the solve button and type that in equal to 0, comma x. Then third will be to make our number line and only do points that are in between negative 1 and 3. So if you got like x equals 7 as a critical point, that isn't in between negative 1 and 3. So only include your points that are in between there. And then fourth, you would basically plug in the x values using your calculator to get the y values. And then fifth would be you report the absolute max and min. So if you want to try these tonight before the warm-up tomorrow, you can. Otherwise, we'll be doing them in class tomorrow as part of our warm-up. So the only one that's a little bit tricky on the solve would be these trig ones. And so if you want to, what you can do on the solve for the trig ones is you do the derivative equal to 0, comma x. But then at the end do at, and then type in pi over 2 less than or equal to x less than or equal to 2 pi. You can actually do that for all of them. And if you do that for all of them, then you'll only get critical points that are in between the domains. So it's actually good practice anyways. So go ahead and try these, and we'll see them tomorrow in the warm-up. And yep, that's it.